This is Physical Chemistry. Part 3, Quantum Chemistry. Chapter 15, Using Quantum Mechanics on Simple Systems. Section 15.1, The Free Particle. First, let's review the time-dependent Schrodinger equation. H psi equals IH bar times delta psi over delta t. H is the Hamiltonian operator. H has a physical meaning, the total energy of the system. Psi is the wave function of the system. I is the square root of -1. H bar is the reduced Planck constant. H bar is h over 2 pi. Delta psi over delta t is how the wave function of the system changes with time. For a one-dimensional particle, we have psi as a function of x and t. X is the position of the one-dimensional particle. T is time. Now let's further simplify this time-dependent Schrodinger equation for a one-dimensional particle to a time-independent Schrodinger equation. We can do that only if the potential energy is independent of time. V is the symbol for the potential energy. If V is independent of time, we can write out this equation. Over here we have the kinetic energy operator being applied to psi. This is potential energy operator. And over here E is the total energy. And this is the right-hand side of the time-dependent Schrodinger equation. Let's try to separate the variables x from t. We conjecture that the wave function of x and t is simply a product of a wave function of x times another function of time. This separation of variables leads to this equation. So it comes from here. We just replace this uppercase psi of xt with the product of this lowercase psi of x and another function of time. So this becomes this, and this becomes this. Now we realize this lowercase psi of x does not depend on time. So we can take it out over here. After we do that, psi x appears on the left-hand side and also on the right-hand side. They cancel. So we have E times the function of time is equal to IH bar times the first derivative of the function of time. By solving this differential equation, we can see this f function of time is e to the power of -I et over h bar. What about this lowercase psi? After we get this equation, we'll see clearly over here. We just plug it in. Plugging in here, we'll see this E times psi x is also equal to H psi. And H is the Hamiltonian operator. H is the sum of the kinetic energy operator and potential energy operator. So we get this equation. This is the so-called time-independent Schrodinger equation. It does not involve time. So over here we have kinetic energy operator being applied to psi. This is potential energy operator being applied to psi. The result is E times psi. E is a constant. Now let's further simplify this equation. Let's assume we have a free particle. Here free means this particle feels zero potential energy. V is 0. When V is 0, we have this equation. How do we solve this equation? First, we simplify this. The second derivative of psi is simply -2 me over h bar squared times psi. This still looks a little complicated, so I'm going to replace this with just -k squared by defining this k to be the square root of 2 me over h bar squared. Right? What's the physical meaning of 2 me? The physical meaning of 2me is the magnitude of the momentum of this particle. You can look at this derivation here. Over here, 2me is simply 2m. The square root of 2me is simply the square root of 2m times the kinetic energy of the particle, because we have a zero potential energy, so this total energy is kinetic energy. I just replace this E with kinetic energy, and kinetic energy is half mv squared. And then we combine this, you'll see it's just the square root of m squared. V squared is just the absolute value of mv, and mv is the momentum. So really this k is proportional to the momentum of the particle. The value of the k is the magnitude of the momentum divided by h bar. And k times h bar is the momentum, is the magnitude of the momentum. Therefore, the momentum of this free particle is either kh bar or negative kh bar. Alright, so now again, let's look at this equation. It's simplified. The second derivative of psi is itself multiplied by negative k squared. Well, what kind of wave functions can satisfy this equation? It's very simple. We have two different kind of functions. E to the power of ikx, e to the power of negative ikx. You can just plug this in here. You take the second derivative of e to the power of ikx. The result is ik times e to the power of ikx. And ik times ik is negative k squared. You can verify this as well. The second derivative of this function is negative ik times e to the power of negative ikx. Well, negative ik times negative ik is also negative k squared. So you can easily verify that these two equations satisfy this differential equation. Well, we have a more general solution for this free particle. This is because these two are both eigenfunctions of this second derivative operator, and they have the same eigenvalue. Therefore, we can just do a simple linear combination. That means we just multiply this by a constant, multiply this e to the power of negative kx by a constant, and we sum it up. Again, a plus and a minus can be any number. A plus and a minus can be even complex numbers or imaginary numbers. They can be positive, they can be negative, real numbers. They can also be any complex numbers. So this is the general solution for a free one-dimensional particle. And if you plug in this general solution to the time-independent Schrodinger equation, you'll see this equation holds true.